Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast problem, we are asked to react 1,3-butadiene with Br2. We are told at minus 15 degrees Celsius two products form, product A at 46% and product B at 54%. At plus 60 degrees, 90% of product A forms. You are asked what are the structures of A and B and explain. If we take a look at this reaction, we can react 1,3-butadiene with Br2. Br2 will attack this molecule. It will be polarized because Br2 is a polarizable molecule, and it will form an intermediate called a bromonium ion, a bridging bromonium ion. Markovnikov addition. Now, the bromonium ion intermediate with the bridging bromine actually interacts with the carbon so that you get trans addition when attacked. But what's interesting is we can get reaction with the Br2 so that Br minus can attack here. And it can give us 1,2 addition. That addition is trans. But there's free rotation. And we get a 1,2 addition product. We can also have the Br minus attack at this carbon, and the pi bond will shift, breaking the bromide. And we'll get the 1,4 addition product. Now, if we examine these two molecules, we can quickly determine that the 1,4 addition product is the more stable alkene. And the 1,2 addition product is the less stable alkene. Normally, the more stable would predominate under all conditions. But if we look at the potential energy diagram for this molecule, and I really don't have a lot of room, so I'm going to rub out the question here. I'll try to draw it at the top. I'm going to draw it from the bromonium ion. There we go. So let's draw a potential energy diagram here. The bromonium ion is here. The more stable, I'm going to use black to represent my 1,4 addition product. Okay. It's more stable. And I'm going to use red to represent the 1,2 addition product. Now the 1,2 addition product is less stable for two reasons. One, you've got the less substituted double bond. But two, you also in this case have two large bromine atoms next door to each other. And that can lead to some steric repulsions. So the red guy is less stable. Now it turns out that the 1,2 addition product's transition state is actually lower energy. The 1,4 addition's transition state has a higher energy, and you see this crossover in the potential energy diagram. Now when you get crossover like this, this indicates a temperature dependence. And if we consider what happens at low temperatures, like the minus 15 degrees Celsius, at low temperatures we just have enough energy to make it over the red hill. More molecules make it over the red hill than the black hill, and at low temperature they can't go backwards. You're under kinetic control conditions. The reaction's kinetically controlled and the 1,2 addition product predominates. If I check minus 15 degrees, the species that predominates is B, 54%. So this tells me that B is my 1,2 addition product. Now as you raise temperature and you start putting enough energy to get equilibrium control that you can actually overcome the E activation reverse, these larger hills, then the red molecule finds it's easier to go back than the black because the black has the biggest energy of activation reverse, if you like. And so black begins to accumulate. Red molecules get back, more go to red than black, but eventually you start getting a buildup of black. At the temperature of plus 60 degrees, where there's 90% A, the 1,4 will predominate. This is called thermodynamic control because the more thermodynamically stable molecule predominates. So the 1,4 addition product A is product A. So there you have it, the solution to the question. Because of kinetic and thermodynamic control, we can identify products A and B. B is the 1,2 addition product, and A is the 1,4 addition product. Well, I'm Dr. Brian Lloyd. This is my Scribblecast. Thank you very much.